All right, so following the molecular orbital theory, what you end up with is MO diagrams. And so in MO diagrams, we generally ignore core orbitals, and we only worry about valence ones. Right, and so remember, these are the linear combination of atomic orbitals, of the valence ones anyways. And so when we do this, they give us molecular orbitals. And all of this stuff is all about maximizing the attractive interactions, so right, proton-electron interactions, and minimizing the negative repulsions, right, electron-electron repulsion. So it's all just about figuring out what the molecule looks like when it's at its most stable. And so here's an example of an MO diagram, a very simple one. So let's just deconstruct the parts here. You have your atomic orbitals on the left and the right. So this would be, just kind of A by itself and A by itself. And then these two are going to come together and their orbitals are going to mix to form molecular orbitals. You see every orbital has the same amount, right? So these two 2s orbitals mix to form two orbitals. And they always create an even amount or the same amount of bonding orbitals as they do the anti-bonding orbitals. And so on the left and the right are the orbitals of the atom by itself, and in the middle are the orbitals of the molecule. And so remember what molecular orbital theory says is that the electrons belong to the whole molecule. And so if you want to react these electrons, you have to think about where they're at. So that's a very simple one. Let's take a look at another simple one. And so these actual energy levels depend on what elements you have. So this next picture is just a series of some diatomic elements. So in this case, we're just considering two of the same element, still very simple, but you can see the energy levels don't always stay the same. So you can see here, it just goes from left to right, lithium, beryllium, boron, right, going across the periodic table. And you can see that the orbitals actually change quite a decent bit, right? And so the first thing you do is you make your MO diagram. The second thing is you fill it with valence electrons. So let's take a look at what can a simple version at least tell us. And so the first thing you can predict is bond order. So similar to Lewis structures, where we predicted some bond order, molecular orbital theory is going to be much more accurate in terms of the actual bond order. And so in molecular orbital theory, the bond order is equal to the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbital all divided by 2. And if you get a 0 here, that means that it's unstable, that these two compounds will not bond with one another. So notice here we start with the 2s orbital, and so what we're talking about here is just the valence orbitals. And so we'll just talk about valence electrons. Let's just fill it in for N2, O2, F2, and Ne2. Let's start with N2. Nitrogen has 5 valence electrons, so a molecule of N2 would have 10 valence electrons. Let's fill it up with 10 electrons. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Filling the same way we did with the orbitals, right? And so you have to pay attention here. This one's a bonding orbital. This one's an anti-bonding orbital. Bonding orbital bonding orbital, anti-bonding orbital, anti-bonding orbital. And so you want to figure out the bond order of this. Well, we have 8 electrons in bonding orbitals minus 6 in anti-bonding orbitals. Oops, my bad. Only 2 in anti-bonding orbitals, right? These are the only 2 in anti-bonding orbitals. So 6 minus 2, and then don't forget to divide by 2, is equal to 3. So MO theory predicts that N2 will have a bond order of 3, which if you think about Lewis structures, yep, that agrees with that, and it agrees with it experimentally as well. Next up, O2, 12 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons. And so here we still have 8 valence electrons in bonding orbitals. And now we have 4 electrons in anti-bonding orbitals because these 2 electrons up here are in anti-bonding orbitals. Notice how it's pi star. Remember, the star means anti. So 8 minus 4 divided by 2 is equal to 2, and so it predicts O2 is a double bond, which is correct experimentally, and the same thing as our Lewis structure states. Next up, F2, 7 valence electrons, so F2 would have 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so here again we have 8 valence, or 8 electrons in bonding orbitals. Now we have 6 in anti-bonding orbitals. We have the 4 up here, and then these 2 down here. So 8 minus 6 divided by 2 is equal to 1, and F2, of course, is a single bond. And then finally we have Ne2, and so neon has 8 valence electrons, so this will have 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 electrons there, so we have 8 in bonding and 8 in anti-bonding, so 8 minus 8 divided by 2 is 0. And so this tells you that neon will not form a bond with itself. So N2 or Ne2 is not a thing. It does not exist. So you can see here how it agrees with our Lewis structure, and they both kind of predict the same thing. So you're thinking, why would I use MO theory when Lewis structure is doing just as well? Well, let's take a look at another property, magnetism. And so our question here is O2 paramagnetic or diamagnetic? Remember, paramagnetic means unpaired electrons, diamagnetic means paired electrons. So if you take a look at the Lewis structure of O2, it looks something like this, and it looks like all the electrons are paired. And so you would predict that it's diamagnetic. That is diamagnetic. But let's take a look at the MO diagram of O2. All right, so that was a struggle. Anyways, you see in this MO diagram on the left and right, we have our atomic orbitals. In the middle, we have our molecular orbitals. So here we're talking oxygen, oxygen, and then here we're talking about O2, the molecule. Oxygen has 6 valence electrons, so we need to add 12 total valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so you see in this MO diagram, O2 has 2 unpaired electrons, and so this predicts paramagnetic. So Lewis is predicting diamagnetic, MO theory is predicting paramagnetic. Which one's real? Well, in real life, O2 is indeed paramagnetic. And so in this case, molecular orbital theory is better. And in almost every scenario, molecular orbital theory is better. It's the closest to the truth we can kind of get. It's just that it's a pain to calculate. Let's take a look at another component, resonance. So this is another limitation of Lewis structure. So we're talking about O3. Ozone, when you talk about the Lewis structure, the molecules you're going to come up with is something like this, where you have this single bond on one side and double bond on the other side. But since we arbitrarily chose one oxygen to have the double and one of the single, we can flip it. And so what we can do is draw resonance structures. And so resonance structures are a way to kind of mask one of the weaknesses of Lewis structures, and that it's basically in real life, this is not a single bond and this is not a double bond. They're really kind of 1.5 bonds each. And so molecular orbital theory, because it considers the orbitals to belong to the molecule, does not have this problem of having to draw resonance structures. In molecular orbital theory, it predicts exactly what would look like, right? So your electrons belong in this orbital that spans all 3 oxygens, right? So these are your 3 oxygens right here. And then the blue and the red is the molecular orbitals, right? So it says all pi electrons are shared, right? And so both of these oxygen-oxygens bonds are the same. And so in terms of our class, we really won't touch on molecular orbital theory, but I really want to kind of hammer the point that molecular orbital theory really is kind of the best. So there's many, many, many things that molecular orbital theory will predict that Lewis structures cannot. That's just beyond the scope of this class. And so at the end of it, the molecular orbital theory is almost always correct. If it's not correct, then chances are you did the math wrong somewhere. So I just want to show you a picture of a kind of more advanced molecular orbital theory. And so this up top here, this DFT-B3LPY, that's just basically the program that they're using to figure out the calculations of these numbers. But you can see on one side, you have the mixing of orbitals from one atom and the mixing of the orbitals of another atom to form our new molecular orbitals. And so the great thing about molecular orbital theory is not only can it tell you what these orbitals look like, it can tell you the exact energies of these orbitals, which is related to the reactivity of these compounds. And not only does it tell you the energies of these orbitals, it tells you what these orbitals look like. So in this case, one of the more important orbitals would be this one right here. And so you can see that it looks different. So if say you wanted to react this molecule with something, you could see what this orbital looks like, and then you could predict its reactivities. But all of this is kind of way beyond the scope of this class. Pretty much all you'll be asked to do here is to fill in molecular orbital diagrams and tell me the bond order and whether it's paramagnetic or diamagnetic. And so that's it.